using deep learning method for vehicle detection on unrectified fisheye images. Fisheye images are images with wider field of view. These are most commonly used in automobile to render 3D surround view to the driver. Traditionally, development of object detection is done on flat images, and most of the available datasets and training methods use the same. With the use of fisheye images, we can reduce camera usage and perform object detection on a wider area. A number of approaches have been taken previously to solve this problem, such as using a multitask perception network by researchers at Valeo and implementation of spherical cross-correlation filters by researchers at University of Amsterdam. Since there are a large number of datasets and pre-trained models for object detection on flat images, we set out to create a method to convert fisheye images to flat images and then to train a segmentation model onto it and measures its performance. We compare this performance against a scenario where the same model was given direct fisheye images. For conversion of fisheye images to equirectangular images, we first need to convert fisheye image to a spherical coordinate system. As shown in the image over here, for every pixel in the fisheye images, an equivalent point in the equirectangular images were determined using the equation shown. The idea is similar to converting a globe to a flat map. We developed a transformation model and implemented a code to run through a batch of images. A sample output of this conversion and the challenges we faced are shown over here. For the model, we used the standard UNET architecture along with performance metrics such as dice score, IOU, precision, F1, and recall. We started out with commonly used hyperparameters for UNET architecture, along with RMS-prop optimizer for quick convergence. We used binary cross entropy as a loss function because we only used one class for detection, and the batch size was chosen keeping the memory and GPU constraints in consideration. For approach 1, we can report that the model converges in about 30 epochs, that is, no improvement in dice score beyond that. Whereas for approach 2, we also see a convergence by 30 epoch, but the dice score value is much lower than approach 1. Overall metric for these two approaches can be seen and is reported in detail in our report. An example of detection done by these two approaches are shown over here. The image on the left shows an input image fed to the model, whereas the image on the right shows the prediction of the UNET model without using any transformation. These are the same images but with the transformation method applied, that is, applying transformation prior to feeding it to the same UNET model. We can see the prediction area in the transformation method is much lower than the previous method. Conclusion. Transformation method bears less on every metric when compared with using direct fisheye images with UNET model. This poor performance can be attributed to a number of limitations of our method, which we plan to modify moving forward. We have identified a number of methods to improve performance of transformation, such as using inverse mapping, training models with bigger dataset, comparing performance of model other than UNET such as DeepLab v3, etc. A detailed discussion on the performance and future actions is available in our report.